attempt to look on the night sky was a typical entertainment for the humans even before substantial civilization was developed, right? And just as a fun, looking on the night sky, or as modern science fiction followers, it needs a map, and one needs to, like, if we have any equipment to travel between skies, we need to navigate between them, right? And there are so many of them. So it's very far from my primary interests and knowledge, but basically, to orient there, one can follow the line that between centers of the Earth and Sun, and this line makes a trajectory on the night sky which repeats every day, and this line goes a little higher or lower during different seasons, and there are constellations that can be recognized, right? So I probably will need a help of those who speak Latin to help with the names of the stars. So, any volunteers in addition to Adam? Okay, so can you just start from the beginning and give few names? Probably all 12 or 13, but as much as possible.
Start where?
Huh?
Start where?
Just follow the line and quickly name these white constellations.
Okay. Aquarius, Capricornus, Sagittarius, Scorpius, Libra, Virgo, Leo, Cancer, Gemini, Taurus, Aries, and Pisces.
Yeah. Okay. Yeah. Thank you, Joe. This little map is simplified, just and it maps same as globe. It maps all 360 azimuthal and 180. Here how it looks more specific, and we do need a space between Gemini, which means twins, right, and Taurus, which means NDSU bison, right? So between them and a little down, there is a constellation of Orion. So if you look here, here is Taurus, here is the twins, and here is the Orion. It looks like a little X letter, right? You recognize it. And this constellation of Orion, as all constellations, are typically were imagined by ancient observers as a symbol of some character from mythology. So it is a hunter with like sword, keeping the skin of an animal that he hunted. And if you look deeper in Gemini and Taurus, there is Orion, and one can imagine. Let me try to draw, although it will be not a spectacular drawing. So, like a hand, face. Here he has a sword, and here in other hand he carries the skin of an animal, right? So if we follow the tip of a sword, there will be a very unusual thing that can be observed. Like here in city, it is not as easy to observe because we have noise from streetlights. If you go into desert or on a mountain, there will be an object that one can observe with naked eye, but it is not a point as a star, or not a circle like a planet. It will be like a dust in the area, so which is referred to as nebula. And this is one of the biggest nebulas. So on the tip of the sword of Orion, it's called Big Great Orion Nebula, and it has some astronomical names, M42 or NGC 1976. And what is the color of this object? How would you tell? Just tell what you see. Purple, blue. It's a little bit more purple, a little less blue. And this one is done with from Hubble Space Telescope, which has no noise from atmosphere. If you look from the Earth, it will be less blue, more purple, more magenta. And here is the question that we will try to answer: why it is pink or why it is purple. And before we go forward, I want you guys to help in navigating through stars. So this little arrow helps us to follow the, you see Orion. Here is on the shoulder, it's Betelgeuse. Keep going toward the star. It's a little equipment with accelerometer for twins, Capricorn. So follow the arrow line. So go to its moon, not against, but towards the arrow. Okay. But Virgo, like a girl. Yes, but we'll go, and now just move a little down. You see here is a sword, and here there is a little purple thing, right? So with the it's not very visible, but it is the one that we are looking at. The question that we want to answer during the meeting is why it was purple color. Okay. And it deals literally with the little assignment that I passed through. So, we are going to make another experiment, and the equipment that is distributed will help to go over it. Just in case if something fails in an experiment here, I'm going to show how it should look like. So we are going to make a $10 worth spectral analysis, and you will see that the source of the hydrogen, emitting hydrogen, is decomposed onto components that contribute to its spectrum, right? And those values in nanometers you are plugging into table and do some manipulations to get the answers. Make sense, more or less? Okay. I think you will see it on the second screen. And those who are online, you also see this little stuff. Okay, so this little piece, do you see it enough? Right. So this is a high voltage source with a vacuum tube filled with hydrogen, right? And it is by high voltage, it excites it above the ionization limit, and then as electron recombines, it jumps between different energy levels, and by jumping through levels, it releases energy in form of optical quanta. Now, there is a way to demonstrate this decomposition in several ways. So this one. So one of them is to look through the diffraction grating, and another's, yeah, it will be not as visible. So those who are online will not see the full beauty of the thing, but I think if you do think in class, it will be still quite visible. Okay, here is the equipment, and one can make an attempt to look onto the source. Do you see any change when putting in and off? Can you explain what you see? But can you just in lay language tell what is visible? Like, what is the change of the picture by putting this diffraction grating on and off? Yes. And how many lines do you see in non-repeatable? There are satellites on the left and right, but how many lines do you see? Okay, I see only 3, but if you see 5, it's good. What are the colors of these 5 lines? Purple, pink, magenta. Okay, everyone agrees? So if you have these little slides, you can orient them in the horizontal way, so that grading goes parallel to the source, and look on the source through it, and try different angles. So in addition, you can also try looking onto the source through this cheapest possible spectrometer. So if you look on this tool this way, you see right angle, far side. So one should orient it far side to the right, and look this way. Okay, and then there is a little slit. So one should aim, so the line from the pupil to the slit goes directly to the source of light. And then after looking inside, you will see the numbers. So it's graduated to measure wavelengths in nanometers. So try to record what you see approximately. And when we go on the next slide, you see it here, and you can measure it a little better, and then pass on the equipment around and record it into the table. So like wave lengths starting from bigger to smaller. So the one 650 something first. So everyone got a chance to measure, right? Yep. I'm putting lights back. Just trying to bring cell phone closer to the pupil of this equipment, and it is what I saw. So like maybe 660, 450, and 390 or 400, like numbers. Okay. This is what is inside of these devices that you looked. So source, slit, either prism or grating, and here are the numbers that you see. So you can use yours if you want to be very pure, fair scientist, or you can cheat a little and take these numbers. But there are several observations. So the offset between lines gets smaller, right? And right here, it hits the range of human visibility, visible range. There is hypothesis that there are additional lines to follow this progression. In the task for your little assignment to find what is the wavelength of the next line based on like continued progression. Where will be the next line? So in 19th century, the Angstrom, the scientist who was who is memorized by humankind via the units of length, did measure this spectrum with high precision on one hand. On another hand, there was a high school gymnasium, girls' gymnasium geometry teacher with last name Balmer. And he was considering himself as a mathematician and geometry professional on one hand. On another hand, he was reading ancient philosophers such as Pythagoras, who like designed this right angle triangle theorem. And following this Pythagorean ideas, Balmer was believing as his personal philosophy that everything in the world can be explained with integer numbers. And he was proclaiming it in front of people. And once his friend, who was a physicist, decided to make a joke with him, like, you're telling that everything in nature can be explained by natural numbers. So here are experimental data on visual spectrum of hydrogen emission. What are your natural numbers? How can you do it? So it was a challenge. And then Balmer decided to play a little bit and solve this problem. So he recorded these numbers that starting from 660 something, and then you have better numbers. And then he came up with this pair of equations that are opposite to each other. So if you plug in this number into this equation, you should give a number that is quite close to integer. If you get next number, apply it to this equation, it will be also quite close to integer. I will not disclose the answer. It will be less intrigue. And then based on this integer, if one invert this formula, one can reconstruct the wavelengths in nanometers back by this equation, n squared divided n squared minus 4. So the task for your assignment is to keep this progression. We have like 3 or 4 numbers, and then one can guess what will be the next one, and then plug in the next one into the equation and predict outcome of experiment that we today in this lab, in this class, cannot do because our equipment and our human eyes do not read UV spectrum. But not very expensive equipment can read UV spectrophotometer, can read and tell. And then we can compare your calculations with actual numbers and see if you are good followers of Balmer. Make sense? Okay, so please invest the rest of your time into just following this assignment. And actually now I'm starting the lecture, but you can lean back and fall asleep or concentrate on your assignment. I will just entertain you with lots of equations, which if you think they're helpful, you can look them later on fast forward remote, or you can follow right now. So I'm trying to squeeze like 40 slides in 10 minutes. Okay, so the expected outcome of the academic part of the lecture are the following numbers. So energies of eigenstates of electron and hydrogen atom in atomic units are equal -1/2, -1/8, -1/18, and they're numbered like 1, 2, 3, 4. Atomic unit is approximately equal to 27 electron volt. So it's about 10 times bigger than the UV to visible border. The electron which revolves around an ion in quasi-classical way as a Bohr atom has different radius. So this is specific information for my SSI and partial information for Joe. So depending on angular momentum, whether it electron revolves quickly or slower, if it revolves slow, it will be quite close to the nuclei. So x-axis is position from distance from the center of nuclei. If it revolves quicker, there will be a force, this kinetic energy that puts it away from the center. And here will be number 2 is the second radius. If one revolves quicker, it will be even further. And you see there are minima of the energy of an electron as a function of the distance for fixed angular momentum. So depending on angular momentum, there is a dependence of how energy of an electron depends on distance. And the minimum in this curve indicates what will be the actual energy of eigenstate of an electron. This is not pure quantum theory as we were studying in this course. We are doing a little bit obsolete Bohr model. But the beauty is that it can be squeezed into a short time. Full solution of hydrogen atom was partially presented in previous lectures, but it takes much longer time. So by looking on the minima of these potentials here, there, and here, one gets progression -1/2, -1/8, -1/18, and they are shown on the y-axis. So electron revolving around has distance, angle, and velocity. If the distance from center, if the radius vector changes over time, then vector of velocity is the derivative over time of this vector, right? So the vector of velocity keeps the same length, but changes the orientation in space. So the change between this two vectors of velocity is dv, which is oriented, so change of velocity, perpendicularly to velocity. And change of velocity, if we make an increment of velocity in respect to time, it will be acceleration. So from this little geometrical argument, you see that the acceleration for circular motion is oriented toward the center of rotating object, right? So acceleration, velocity, and radius are all perpendicular to each other. Now one can define angular velocity as the respectant one over the period on one hand, and on another as velocity divided by the arc length of the whole circle. So if we do differential calculus and use complex variables to follow the trace of our tip of the arrow on the surface, here is a better calligraphy, on the surface of the circle. So radius is the initial radius times exponential I omega t, right? With real and imaginary will be x and y projections. Make sense? If you take a derivative of exponential, we just put I omega in front. So the real and imaginary parts will be projections of velocity. If you take a second derivative, we got the omega up front once again. And then we see that real and imaginary projections will be the same as for the radius for circular motion. So the radius and acceleration are equal to each other with precision up to a constant minus frequency squared, right? So tip of the radius and tip of acceleration rotate with the same speed. This thing is used for von Braun wheel, or idea of very long lasting space station where humans do not get their bones dissolved as it happens now due to acceleration due to rotation. So if we, I don't know if our life will last long enough to see it, but it is a natural way for space travel to make a wheel that rotates, and there gravity is needed to train muscles. Without gravity, why space travelers cannot stay there longer than like a year? Because bones dissolve and then you will not survive on the Earth. You need gravity and exercises. So and it uses same like acceleration because of the rotation. And there were several science fiction visualizations. I think it was ancient movie made in 1968, Odyssey 2001. So we are much older than their. It's retrofuturism. Yes, not yet there. So force is oriented backwards, right, toward the centrum. Okay, 8 minutes more. Now, if we want to express the kinetic energy of this rotating object, and we accept the concept of angular momentum. So angular momentum is radius times momentum. The angular momentum is assumed constant if it is if there is no damping. So and then velocity is angular momentum divided by mass and radius. If you plug in this velocity into our standard definition of kinetic energy, mv squared over 2, it will be angular momentum over 2 mass times radius squared, same as we discussed like a week ago, right? Angular momentum squared over inertia. So if we look on it as a function of radius, if angular momentum is fixed, it means kinetic energy decreases as we go away from the center, right? So if I take off my belt, put something heavy there and start rotating around my head, the kinetic energy will depend on the length of the belt, right? But it will be positive, plus sign. Now let's look on the Coulomb force. So all charges attract each other. So +1 proton, -1 electron. In atomic units, they do not have, atomic units are beautiful because this 1/4 pi epsilon vacuum permittivity, charge 1, charge 2 over 1, it will be 1. Therefore, one uses atomic units. So -1/r. So the attraction, Coulombic attraction, decreases to 0 if the distance is far. It is maximal if they are close, and it has a negative sign, right? Everyone accepts. So here is just introduction of atomic units, which maybe I should have introduced at the very first lecture of the semester, but probably you would not be happy to hear this boring stuff. So total energy is kinetic plus potential, right? Kinetic is positive, potential is negative, and kinetic energy depends on the angular momentum. So how can we find stationary trajectories where electron will not change its behavior over time? We cannot say that kinetic and potential must be equal. We need to say that change of the energy over manipulation of radius should be infinitesimal, right? Stationary means things do not change. So the most healthy way is to look on this repulsive and attractive forces and explore the derivative, where the change of energy over radius is 0, right? For given value of angular momentum. So here's 1 over r squared, here 1 over r. If we practice this derivative, right, we need to remember what they are. So by taking derivative, power increases or decreases? Decreases, right, thank you. So we have 1 over r third, 1 over r squared, right, for these terms. And then if we solve, so this derivative equals 0, we cancel everything is possible and find that this stationary state will be correct if so here is second power, here is the third, if radius is equal angular momentum squared over mass, right? This is an important and beautiful result. So radius of the orbit is literal function of the quantum number of angular momentum, which is quantized. And angular momentum in atomic units, it changes as 0, or no, in Bohr model, not 0, 1, 2, 3, and then mass of electron is 1 in atomic units, and then the radius of Bohr's will be 1 squared, 2 squared, 3 squared, so it will be radius of expanding size. Okay. So in atomic units, mass 1, Planck constant 1, so L squared. So if we want to visualize it, we can plot this h energy as function of radius for different angular momentum, right? So one line, and it shows minimum closer to the center of ion. So it's 1 in atomic units, or half angstrom in our units, like 4 atomic units, which are about 2 angstrom, and so forth. If we and these thin lines are kinetic energy, right? Which gets a little bigger and bigger, and therefore the minimum is pushed away. Now, if we look on the energies of this minima, if you just plug in this distance equals L squared into our Hamiltonian operator of energy, we plug here L squared over it will be L to the power 4, and here L squared. So we can practice, put a common term outside of the bracket, and have this 1/2 minus 1, which will be minus 1/2 times 1 over L squared. So the energy of electron in the nucleus, according in the frame of the Bohr model, is 1/2 1 over quantum number L squared, right? So if L equals 1, it is just minus 1/2. If L equals 2, it is 1/2 times 1 over 4, 1/8, right? Okay. And yes, so energies in atomic units. One can get back into more realistic values of energies, and here are schematic diagrams of these energies. So like orbits, and in the textbooks, one puts them on linearly scaling radius, which is wrong. Radius increases quadratically. It will be just not enough to have a poster wallpaper big size. And if one draws energies, so you see it's the same progression. Minus 13.5, it's minus 1/2 in atomic units, minus 3.4, minus 1.1. And then if we discharge ionized hydrogen, it will just jump back from level to level. If you look from the state number 2 to state number 1, the energy difference will be about 10 electron volts, which is far in the UV, so we will not able to see it. But if you look for transition from 3 to 2, it will be about 1.8 electron volts, which is red color that we see. If you look transition from 4 to 2, it will be, well, here it shows greenish, but we saw it's more like cyan, right? If you look from 5 to 2, it will be more like purple. And there are additional lines, one of which is already in the UV range. This wavelength of this transition is assignment to find in your little sheets, right? So the transitions that go to state number 1, they're called Lyman series and they're not visible. The ones that end up in number 2, they're called Balmer series. And before this stuff, like about 50 years ago, 50 years before Bohr theory, it was predicted by this mathematician. And no one remembers his mathematical works, only this stuff. And then the next one, Paschen series, is in the infrared. Okay, spectrophotometer. In the second column, you get numbers close to 3, 4, 5, 6, right? And then by intelligently projecting, you see the next number should be 7. And if you plug in 7, you're getting number a little smaller than 400, which is beyond the range of human visibility. So congratulating you with a success. At least in this small problem, you fulfilled the main goal of this course, predicting outcome of an experiment. Meeting is done. Everyone is welcome to disconnect and depart. And from now on, we will put more focus on the projects.